Good morning, students. Welcome to week number, actually, this is an extra lecture to make up for week 8. What in the world are you doing here on a weekend? Why are you here? You ought to have fun and relax and recover from heavy partying on Friday night. I'm not happy with you. But hopefully I'll make it worth your time. We'll finish the lecture about computer taxonomy. I'll go in detail about some of the homework solutions that you should have provided in homework number 2. You were lucky, you had a very benevolent grader. Good that I didn't do the grading. It would have been way tougher, but you lucked out. That was my risk. But the main thing is that you learn something. So 2 of the key questions that I intended you to demonstrate we'll discuss today on the whiteboard with pencil and paper or whiteboard and chalk. And then, hopefully fairly soon, we'll talk about what I call juicy system programming stuff. For and exactly how you create a process, how you say, I don't want to create this process, I want to create another one. And chances are that will go way beyond our allocated time. We should end about 10 minutes before 12 here. And we'll continue then on Monday. And I'm anxious to start a totally different topic, and that is cache architecture and how to use a cache in the most performance-enhancing way. That'll spill into week number 4 and week number 5. First, a couple of announcements. Our grader. So the grader is overwhelmed. Way too much work for the grader, and the university's principle of allocating time and paying for it, they don't line up. So I have to make some changes. I don't know exactly what the changes will be, but chances are you will get, it'll come across almost like random graders. It's either the grader or the TA or I that will grade your future homework. So I have to find some solution so that the grader won't be jeopardizing his own studies. You can't do it anymore at that pace. You are too many. I thought in the first lecture, in the first week, I would have scared half of you away. You were blockheaded and consistent and persistent. You didn't run away. Well, at least most of you did a poor job. Next time I will scare students more. I'll also simplify the remaining homeworks, 3, 4, and 5. Not the homework assignment itself, but the way that I can measure whether or not you did a good job, correct job, or not, more numerical. Is the answer 7? If so, then it's okay. If not, then you get a deduction and so on. So I need to somehow simplify it so that the grading process is not so involving an understanding of what you did and an evaluation, how well you did, and then giving you a grade, but way simpler. I don't know yet how to do it. So we'll still have class on Monday next week, but on Wednesday next week, it will be the grader who will be, the TA who will be conducting class. It's about the topic of assembler, in this particular case, x86 assembly language, and in this particular case, there are many assembly languages for the x86 architecture. The one that the grader will be talking about is the Microsoft assembly language. If you look, for example, if you run on an Intel-based computer and you do a C or C++ compilation with the option of show me the assembly code, you see a totally different assembly language. It's the GNU assembly language with a register name %, AX. In Microsoft, they are simply called AX. There are minor differences, but don't be confused by the fact that any manufacturer for an assembler has their own syntax. Now, the target bits that they have to produce for the x86 architecture is always the same, but the assembly language that allows that mapping is dependent on the manufacturer. Similar to programming languages. Some people prefer C, some C++, some Java, some who knows what. The ultimate bits always have to be bits that are executable on your target computer. So again, Monday I'll teach again, and hopefully by then we're already in the middle of caches, or at least at the end we'll be in the middle of caches. And the grader, sorry again, the TA will teach on Wednesday about Microsoft Excel language. Okay, a couple of warm-up questions. It'll make more sense in about a week. But just probing your background. What is a cold cache? And you can easily deduce it certainly doesn't have much to do with the temperature, putting your finger down, this is cold. Even though there might be a mild correlation. Yes, what's a cold cache?
Cold cache is the cache itself that hasn't been filled.
Okay, you're moving in the right direction. There was another answer somewhere here. What's a cold cache?
I was saying, you're going to say basically the same thing, just hasn't been initialized, so it doesn't really provide a performance boost.
Okay, strictly speaking, what you're saying is correct. So once you start execution, you will have a processor. It won't have done much work yet. It just will begin soon to start the first instruction of the main program. In reality, of course, it has been doing a lot of work for others, like the OS and so on. You will also get a cache dedicated to you on your processor. And the operating system will certainly make sure, well, okay, this cache will be a new cache as far as information is concerned. All of the data lines will have a bit called the invalid bit set to on, meaning whatever bits you find in this line, or that one, or this one, or this one, they're all invalid, meaning there is no good data in it yet. Once you're executing your program, there are some good data in the cache. Whether they are good for the sake of speeding up your execution or not is a different question. Remember the 4 key principles of computing? One of them is things tend to cluster, also in caches. Okay, once you're in an inner loop and you're referring to out of this virtually large, well, on 64-bit addressing, it's a real large addressing space, gigantic addressing space, and for a whole bunch you're twiddling around in this very small area, which is good for caches. The caches warm up, meaning the data that you're talking about, they're still in there. The data that you likely will be talking about in the next 1 or 2 or n instructions are already in the cache. That's what the warm-up means. Meaning there is good stuff in the cache as opposed to nothing in the cache or invalid information in the cache. So that's the difference between a cold cache and a warm cache. So it takes a few steps of execution until your cache, first of all, has interesting data, the data that it needs. And it takes good luck, namely locality of execution, until the cache is warm, so that it provides good data that are fast, swiftly accessible to your program to make the cache warm. Again, figure of speech. Somewhere else in the system, we have a phenomenon that is similar to the cache being cold or warm. What other thing could her possibly have in mind? There's something else which also starts out cold, or, hey, I have no valid data in me. Who is that? What is that?
Memory?
Memory? And what aspect or what angle of memory?
Programs that
Come on.
Registers?
Pardon?
Registers?
No. So who does not know of virtual memory management, or VMM? Who does not know what it is, how it works, and so on? Oh, wow. So none of you have taken, who has taken the operating system course? Okay, all right, no one. Anyway, I withdraw the question. You're running a program, maybe on Unix. Unix views your program as something similar to a program, a process. We'll talk about process more. Now you are a skillful system programmer and you say, you know, I have my main program here, nothing else much, but I want to know what my process number is. How do you do that? Short answer is you include the right library. The library will provide a function get PID, get process ID, which returns an integer type. Format it's defined as something else. It's a process number type, but it happens to be equal to an int. And that returns you a number. And that number is your process ID. Get PID, it's a function. There's a similar function. What is the process ID of my parent, meaning that program which spawned me off? If you have a main program, who in the world could have spawned you off possibly? DOS, you know. So you have even the function get PPID, get the parent process ID in that same library. So you can say, well, here's my main program. I'll wonder what's the process ID of that OS that spawned me off. Strictly speaking, in old C, the main program was actually able to call the main program. So there, you had a different relation, or a more rich relationship of the main program to its parent. It didn't have to be the OS. It could be another invocation of the main program. It's a quirk in older Cs. The principle is still the same. Get PPID means get my parents process ID. We'll talk way more about that once we talk about fork and exec-B. Once you become real hardcore system programmers. Something that happens, it pops up a lot. In the context of execution, and remember, quote, computers always run too slowly, end quote. No matter what you do, speed up the clock rate by a factor 100. Good, improvement. It'll always run too slow. What do architects do? Well, they invent clever tricks, but this is not architecture. What do system programmers do? They say, oh, what's exactly the architecture providing me? Am I taking advantage of the speed up? Lo and behold, I don't. So one of the things that allow you to run faster is the parallelism, or exploiting a second core in a multi-core target machine. And you, as the system programmers, you need to know how to do it, or you need to figure out, is it being done or not? Why are all these other 3 cores idle if this is the only one running and I'm so slow? Okay, that's what the system programmer needs to understand. In that context, you need to understand what is concurrent programming versus parallel programming, or what is concurrent execution versus parallel execution. Now, since you haven't taken the US course, nor the compiler course, I asked earlier who has taken the compiler course. Here in class, I think it's most one. None? Okay. Okay, what's your intuition? Always keep in mind, computers are always slow. Computers are always too slow. Computers are always way too slow. Herb said one of the 4 principles of speeding up computer execution is replication of resources. What does that mean? Adding a second processor, or third, or fourth, or fifth, and so on. So we want to run, how do we want to run our sequential program? Ideally in parallel, meaning executing a sequentially written program, or a program written with sequential execution in mind, on 2 or more processors, for the sake of running more swiftly. So parallel means you have more than one thread of simultaneous execution at one time. Concurrent means you have more than one thread of execution that could execute, but you don't know which of them, this one or that one or the third or fourth or fifth one, is actually running at the moment. Had you more processors, they could all run in parallel. Since you have only 1 or 2 few processors, they only can compete with one another. I want to run, sorry, you didn't get the CPU. I want to run, sorry, you didn't get the CPU. I want to run, okay, you get it. So they are competing with one another, but they could run in parallel. And somebody must have made sure, either the human programmer, at great expense of what is called brain power, or a piece of software that analyzed your program and said, oh, here's a thing called a thread that could actually run in parallel because it's independent. There's another one that could also run. All of this other stuff cannot run in parallel, but at least we have 3 threads, this one, and this one. How many processors do we have? 1. Then they're just competing with one another, running concurrent. Oh, we have 2 processors. Out of the 3, I'll allocate you and you a processor. The other one still has to wait. Oh, we have 4 processors. You and you can run on the processor, and the 4th processor sits idle. Goal is always to enhance your parallelism. The reality often is, we have more processes or threads sitting idle saying, I know, I'm independent of the others, I could run, I just don't have the resources. So all of that in the context of system programming, we are the ones that need to make sure software runs faster than it currently does. Yes?
So what is the hyper-threading?
We'll talk about hyper-threading today.
Okay.
But the short answer is, hyper-threading is the computer architecture trick with silicon to give you the impression that you had yet another processor, while in reality you only have a very narrow subset processor. And under the right condition, it can help you speed up execution. And the point is at a fairly low cost. The cost of having yet another processor there, meaning replicating all of that silicon, so every billion transistors counts a lot. That would be ideal, but chances are you, with your ability to pay, or the manufacturer with their ability to put it all onto one die, they find limits, so they say, we found a special trick. Let's trick this hyper-threads. We'll talk about that. That will be today. Okay, so now you should be warmed up. Okay? You know what a warm or cold cache is. You know what, at least you have an intuition for what parallel execution means versus concurrent execution. Okay, I'll resurrect my old question. If you had used paged virtual memory management, then you would notice that at the beginning of execution, every time that you do a memory access, you have a so-called page miss. The page has to be created or swapped in from a disk. It takes awfully long, and it takes quite a while until all of the key pages that you want to talk to, they are physically in memory. Then execution runs nicely, meaning your VMM system is warmed up, like the cache. But since you haven't talked about VMM yet, and chances are we won't talk about it in system programming. That's all I'm going to say about it. Okay. Who's still not awake? Other than me. Would you do me a favor? Go one more time to the front door and see whether or not somebody is desperately trying to get in.
Yeah, sure.
Our guard is not overly helpful. Politically correct union guy. You have a total list of all of the names that could possibly come in writing right here. No, I don't have it. Okay, that's so, I thank him very much for his services. This pay is good. Okay, let's go on with the topic where we left off last Wednesday evening. We were talking about something, right? Various computers, various computer architectures. And why do we build different architectures? Because computers are always too slow. So we need to build something else which is faster than the previous one. Okay. That's what we're going to do. Who does not yet have a good intuition what is essential about a pipeline architecture? Who is completely fuzzy or fuzzy? Okay, good. So here's a picture to show it what I'm talking about. Who is unclear what is a superscalar architecture? It's actually more difficult. Pipelining is fairly straightforward what it is or what's essential about it. Superscalar is way more fuzzy. So is a superscalar architecture an MP architecture, a multiprocessing architecture? No. No. Good. She's looking at the name. Female, has a brain, so she can deduce from the name. Superscalar means it's still a scalar architecture, but not yet a parallel architecture. But it's more than just scalar. It is superscalar. Okay, from supra, Latin, more. more over. Nobody there?
Nope.
Good. Okay. So hopefully we didn't create any pressure. The superscalar architecture is still, I'm just filling in where we left off last week. The superscalar architecture is still a scalar architecture, but under the right conditions, it has enough resource, either ability or replication, under the right circumstances, to sometimes execute 2 or more instructions at the same time. And that is independent of pipeline. It could be pipelined or not pipelined. But even if it isn't pipelined, and therefore we don't have the parallelism of multiple portions of different instructions are executed at the same time, which is in effect a version of parallelism. Excuse me. Let's totally forget about it. Let's say we look at a superscalar architecture that is not pipelined, but superscalar. There are still occurrences where 2 or more instructions are executed at the same time. Well, what can that be? Well, several answers to that. One answer is, the architects were clever enough to say, well, even a regular old-fashioned ancient computer that your grandparents used, it still has a floating point unit, an integer unit, a fetch unit, a store unit, a control unit. The architects were smart enough or intelligent enough to arrange these different units, maybe the floating point adder and the floating point multiplier, in a way that, given the right circumstances, they're always there anyway. They can be run at the same time. What does it mean, the right circumstance? That means the architect has built enough hardware to look into the yet to be processed instruction stream in a way that it can analyze, oh, wait a moment, that instruction back here is completely independent from an instruction that I'm currently intending to execute, meaning there is no register collision, for example, or there is no memory access. Neither of those writes to memory, and there is no danger memory-wise. Neither of those uses a register that the other one writes. Bingo, they can be done in parallel. Earlier computer architects didn't think about it. Superscalar architects thought about it. Well, let's analyze more than just the current instruction and see whether perhaps they can be run in parallel. Since I already have a floating point multiplier, and I have a floating point adder, and an integer unit, and so on, why not use them simultaneously? That's the essence of superscaling, flavor 1. The other flavor is, man, in reality there's a whole bunch of integer operations being done even when you do scientific computing, meaning even if you do lots of floating point manipulation. Because even if you do FP stuff, you still need to compute addresses, that is, integer operations. So let's replicate the integer unit 2 or 3 or 4 times. And then again, analyze the instruction stream, see whether there are multiple integer operations close together, see whether they happen to be independent of one another, and if so, run them on 2 or more integer units. You haven't replicated the whole processor, therefore it's not an MP machine, but you have added more hardware to it than the original strictly scalar machine, by adding, say, a second integer unit or a second floating point multiplier. So superscalar means you're somewhere in between the uniprocessor and the multiprocessor. You haven't replicated any processor a second time, and yet there are occasions that 2 units or more can run at the same time for the benefit of speeding up your software. That's all. So, just wanted to clarify it a bit more. Vector architecture, okay, we talked about that too. Shared memory, distributed memory. I know we were very brief on systolic array, and it's such an esoteric architecture. You just need to be aware of what it is. It's a particular configuration of multiple processors with a very fast bus connecting them. Okay, there are still a few architectures that you must be aware of, and we cannot possibly go into detail about those. If you want to know more about it, take my 538 class, Advanced Computer Architecture, and then you hear more about it. You'll just get a high-level intro of what it is. One of these architectures is the VLW architecture, very long instruction word architecture. Very strongly related to the LIW architecture, long instruction word architecture. What's the exact difference? A somewhat arbitrary but clear way of differentiating it is architectures that have a long opcode of 128 bits or more we call varied. The other ones that have a long opcode, longer than, say, 8 bits or so, but less than 128, we call those long instruction words. That's all. So let the borderline somewhat arbitrarily be 128 bits. And now, what is LIW or VLIW? I'll just say generically LIW. A long instruction word architecture, an LIW architecture, strictly speaking, is also a uniprocessor architecture. But similar to what we mentioned earlier about superscalar, where the architects found a trick to analyzing the sequential instruction stream in a way that it could determine it is correct now for me to execute two instructions that are close together on two execution units at the same time. Similar to that, the LIW architecture is also a sequential machine, also a scalar machine, but it has one more instruction, and that is the super instruction, or the super duper instruction. That is the LIW instruction, which says, I have a different opcode. My opcode is such that the opcode itself defines I am the special instruction, and in me I have packaged a whole bunch of other instructions, namely some or even all of the regular sequential instructions that the machine already has. So it would be one super opcode, and in there you can say, yep, I want to do a floating point add operation, and a floating point multiply operation, and an integer operation, and a load operation, and a store operation, and an integer increment operation, and an integer decrement operation. All of it at the same time. But the burden to make sure that it's correct to do so, which in general it's not. You cannot simply take your sequential code and say, okay, from here to there we do all of that in parallel. You will get wrong results. And several people do care about right results. So you can't do it. But on an LIW architecture, you have an instruction which allows to do just that, except you, the programmer, or your very smart compiler, has to make sure that whatever gets packaged into that instruction is already provably correct if executed at the same time. Did that make sense? Too long of a sentence?
So the burden falls on the compiler rather than on...
Yes, I'll articulate it differently, but I think you got the gist of it. So, the VLIW architecture has a special super-duper instruction which can do a whole bunch of its operations in parallel. But the burden of proof that to do so be correct is an intellectual burden that has been already solved or resolved by the compiler that emits the code or the human programmer that writes assembly language for this and says, I know this floating point multiply is independent of that one, is independent of the floating point add, is independent of the integer. Oh, I don't have a second integer operation that I can do at the same time, so I put a no-op integer in there. And it's independent of the load operation I do. I don't have a store operation yet, so I put a no-op store in here. I don't have anything to auto-increment. Oh, and I can do an auto-decrement on that integer operation. And all of these, being independent, has to have been proven by your software or by you in order to take advantage of that instruction. This is a very difficult task. That task is called software pipelining. We unfortunately can't do that here. It takes me several weeks to discuss it. In the 538 architecture class we do that too, but it takes a couple of weeks. It's a very tricky method, as you can imagine, because you have to prove that it's correct. But at least you now know in essence, what is an LIW or VLIW architecture? It's like a regular scalar computer, except that it has that one super duper instruction which says all of my execution units that I have, they could actually be run in parallel, all of them, or many of them. Okay, since most of you haven't been professional assembly language programmers, you don't even know what microcode, horizontal microcode compaction is, so well, just ignore it. Okay, so here is a picture of a hypothetical or an abstract LIW instruction. So this machine would have an opcode for floating point add, and a separate opcode for a floating point multiply, and so on. And in addition, it has that other instruction called the VLIW instruction, which allows you to pack or assemble into a long instruction a whole bunch of different sub-opcodes. Plus always one sub-opcode more, which is, I want to do a no-op floating point add. This time machine, even though all of these may be active, don't do a floating point add operation. Or this time, don't do a second integer operation. Or this time, don't do a load operation, or a second load operation. Okay? So you always have the option of no-opping them out, but at least the remaining sub-opcodes that are valid can all be done at the same time. For whom is the concept of LIW architecture now totally foreign? Maybe I emphasize one more point, even though I've made it in different words a couple of times already. I always mentioned the correctness of this working has to be proven by somebody else, not by the machine. The machine is not guilty if things go wrong. For example, if you do an integer operation 1, maybe an integer add, and the result goes into register 1, into register 1. You cannot think that for the integer operation 2, this register 1 could be used as a source operand, and that that source value be the one currently computed here. That you can't do. If you would, you defeat the purpose of parallel execution. Okay? So, if indeed the integer 1 operation says, okay, when I'm going to crank now, because I wasn't no-opt out, I'm going to do an integer addition and put the result into register 1. This one here, I'm not no-opt out, I actually have to do work. Two of my operands are register 1 and register 99. Bingo. And it can fetch those right away. But the value at the start of execution that this one fetches from register 1, and the value that this one computes into register 1, they are totally independent values. I'll give you a trick. I'll give you a hint. The mystery behind it is that the next time around, this is presumably in a loop, the next time around that this instruction executes, then the next time around, the source operand in register 1 used here is the one that previously was computed there. And to take advantage of that in this very tricky way is that technology called software pipelining. Too difficult for a 200 class, but at least you need to know about it. Okay, so that was LIW or VLIW, very high level intro. Those of you who begin to grasp what that is, at least should develop a sense by now, man, the logic to put all of those multiple sub-opcodes in here, hopefully inside an inner loop so that you get real advantage of the speed up of the parallelism. The logic is quite intricate. Now, okay, I always package a little bit of personal experience. So when this kind of architecture was cooked up, that was in the mid-1980s, Carnegie Mellon University had already a special purpose machine, was actually also a systolic array, with a small army of almost a dozen graduate students who were all looking for their PhDs. All they were doing is they were working on a tool, on a software tool, which would automatically generate code for this kind of an architecture. The architecture at the time was built by GE. The machine was called Warp. One of the more successful students, her name is Monica Lamb. When she was finally done with all of that stuff, she got her doctorate, and it was such a recognized good piece of work. She immediately got multiple positions as a computer science prof, one at Stanford University, one at in New Jersey, Princeton, and a couple of other ones. And she was like, oh, which one should I take? Should I take the Princeton one, or, oh, I like California better. So she ended up in Stanford and is still there. Two of the other ones, I had worked with them very well because later on Intel created a commercial product similar to that one, but a bit more powerful, so we had to cooperate with them all the time on an almost daily basis, and I had to make many trips out to Pittsburgh to be at CMU. Two of the other guys that did similar work, Thomas Gross, and the other one I forgot the name, they also had similar experiences, but they came from Germany and Switzerland. They wanted to go back to supposedly civilized Europe, and they both got professorships at ETH in Zurich. Not a bad place to work either. So, just a little personal touch. It's good when you're an old guy like me, you have run around and touched so many different people and organizations and programs. They did an awesome work, these folks. And then we at Intel took advantage of their compiler technology, built it into our own compiler for Intel's iWalk machine, and magically, we had a software pipeline code generator for the Intel iWalk, and believe it or not, it worked. But lots of professorships resulted from it. And as you can imagine, the LLW machines are way too slow. Essentially, they are still what we call single-core computers. Okay, so we need to speed it up. Then pops up in the 1990s the EPIC architecture, the explicitly parallel instruction computing, EPIC. In the early 1990s, Intel and HP said, you know what, everybody uses this Intel architecture. Well, not quite, because IBM at the time made the, what was the name of the famous competitor of x86 architecture? Students, don't you know?
AMD?
In IBM's
Cyrix?
Pardon?
Cyrix?
PowerPC.
PowerPC, yeah. The PowerPC was competing. Intel and HP put their heads together and said, all of this stuff is way too slow. We need to cook up a new architecture, one that at least on the server and high-end server level takes over the whole world, and everybody will move to our new architecture. And that was the EPIC architecture. And they actually did build it at very high cost, beautiful architecture, has one minor advantage, it slows as molasses in January. So, therefore, people say, we are not all buying titaniums, we still continue to buy these old-fashioned, awfully ugly Intel x86 processors, put them into our servers, cool the processors enough so that they can run at a high enough frequency, we get good performance out of those. But of course, contractually, the two companies, HP and Intel, are still obligated for a certain amount of time. I have honestly no clue how long that works. It could be that the obligation already has run out. But they still manufacture this, and it's honestly one beautiful architecture. Again, I won't tell you much about it, other than I give you a few things that characterize it. Let's see. Oh, one of the most obvious things when you write assembly language for the Intel EPIC machine, and I say Intel, but I should say the HP and Intel EPIC machine. It's called Itanium. One of the awesome things is you can write assembly language, one instruction, comma, second instruction, comma, second instruction, comma, as many as you want, or at least one, even that would be a no-op, followed by two semicolons. When it's a semicolon, then the assembler knows to admit code in a way that all of the stuff you have written before is packed into a bundle. Everything in the bundle is executed in parallel. Sorry, can be executed in parallel. You, the human programmer that wrote assembly code, or the compiler that emitted this assembly code, already verified the logic that all of these, floating point add, another floating point add, floating point multiply, integer, blah, 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 and so on, all of those can be executed in parallel and still create the right result. The Itanium architecture says, I have more than one processor, and I execute all of those in one bundle, this one and this one and this one and this one and this one, all in parallel. Now, HP and Intel, they are making progress over time. So today they may have an Itanium, or yesterday they had one having only 4 processors, or 8. That very same code now, even if the clock rate would be identical, that same code can run on the next generation that has 16 processors. Same clock rate, assuming, of course, they will up the clock rate. But if it had the same clock rate, the only difference you notice, wow, it runs way faster. Because the old code already said, this and this and this and this, all of the stuff in the bundle can be run in parallel, maybe 18 steps. Previously, we had only 6 processors that could do it at the same time. Today, we have 12 processors, runs faster. So, one of the key differences, now instructions can be assembled into so-called bundles. Numerous instructions were invented that avoid the conditional branching. Let's get back to our earlier question. Hey, what is a cold cache? What is a warm cache? Why is branching bad for execution? Even though you may have good branch prediction. In other words, I don't want to focus right now on pipeline architecture. Forget about pipelining at the moment. Only focus on execution and branching. But you have a cache. So why is branching bad?
Because the instructions that it thought was coming next are in the cache, but since it's branched, it has to go get it from memory.
Exactly. What's your name?
Ian?
Okay. Exactly. So, the thought of the machine was, currently I'm executing this instruction, the next one I'm executing is the one just right after it. Okay? Move it all into the cache. Now there is a branch, bingo. All of the stuff that I moved in cache, oh, darn, it's all invalid because we branch over there. Okay, start fetching from there. Now we need to go to memory, costly. Then move a whole paragraph from memory into the or another cache line, and then resume the whole stuff. Okay? That's why branching is inherently bad. Branching means branch, conditional branch, call, return, abort, exception. All of these things that change the regular flow of control. Regular means instruction n, instruction n plus 1, instruction n plus 2, instruction n plus 3, blah, 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 and so on. Everything that changes this regularity are referred to as branching. That is bad, because the cache that thought, I'm a warm-up cache, I have close to all of the data that you want already here, accessible in, say, 1 or 2 cycles, as opposed to 100 cycles going to memory. Bingo, wrong thinking. So, instead of having a conditional branch instruction, this machine has a so-called conditional assign instruction. It says, here's the conditional, say, load or conditional compute instruction, which says, if A is greater than the contents in register 3, then do an addition, put it into register 1. Bingo, done. If not, it's a no-op. But at least you didn't do a branch. Normally the compiler would have to emit a branch at the end of the then clause, branching off the else clause, and so on. And with the new instructions on this architecture, much of the branching code is suddenly straight-line code. Not only that, the machine has what is called speculative execution. So here's your favorite if statement. If some condition do blah, 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 blah. That's what I call the then clause. Else do blah, 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 the then clause, the else clause. This machine says, well, you know what? I have lots of processors. Oh, I see. Here are two different bundles. Well, I'll execute them both in parallel. But they are predicated, meaning there is one particular bit which in the end will tell me, of those two, which one is actually valid. And in the meantime, the machine can also execute the if condition. If function foobar returns a value greater than 17, that is a computation, may involve calls and parameter passing and returns. It takes a while before that's known. Once it's known, the predicate bit is set. And these two streams of execution both relied on. And they say, we're executing it, but we don't know whether the predicate ends up true for me or not. And as soon as the predicate is known, then the machine says, you know what, you else clause, we don't need you, just discard what you did. So it warmed up the universe just a little bit, but didn't do any damage. And you, the then clause, you are the one that is true, you need to continue. The problem, of course, is, students, what if that discarded else clause had done a store in memory, in the memory? Okay, rhetorical question. As long as the machine is executing speculatively, it should not do any posts of results. Meaning it can compute into registers as much as it wants. But not store anything in the memory.
Sorry.
There? Anyway, those kinds of things are part of the epic architecture. And another minor thing. If you ever generate code, or if you're concerned about mapping high-level constructs into object code, on a GPR machine, you'll find the fewer registers you have available, the more difficult is the code generation. Not the intellectual effort, that is not difficult. Except you have an intermediate result, you need another register, eventually, oh, darn, I'm running out of registers. What do? I store the current value of this register in a memory location that I remember. Then I have a free register, then I can continue. Oh, now I need to finish the previous execution. Oh, I remember I put something into memory, I bring it back from memory into a register and I can continue. These added load stores are artifacts of the fact that we have too few registers. There's a machine with 1,000 registers. It takes a while before you run out of those. Now I'm giving you a round number, 1,000. It's on the order of 1,000. Plus they are grouped into sub-registers. So there's a couple of hundred floating point registers, a couple of hundred integer registers, a couple of dozen branch registers, a couple of dozen special purpose registers, and so on. But overall, that machine won't run out of registers very soon. Here I mentioned the point. The machine has many registers, not just 64 general purpose registers. And I, of course, mean that tongue-in-cheek. Many architectures have way less than 64 registers, including the ancient, old, ugly Intel architecture, which has only 4, and they are somewhat special purpose already as opposed to general purpose. Plus another 4, but they are even more restricted in use. Oh, I have a typo here. Predication associates a predicate, typically a Boolean value, with 2 simultaneously executed sequences of instructions. Not prediction. You know what branch prediction is, right? Branch prediction is another architectural feature to help avoid that awful stall that you have in a pipeline architecture when you have a branch. A branch predictor says, hi, given the current address, I know already which one will be the next one. By default, it's the address behind it. Very often, if it's a branch, it's the target of the branch. A branch predictor helps the architecture remember those things. So that's branch prediction. This machine also has predication. So it has predicates, meaning Boolean values that say, out of two paths of execution, the else clause and the then clause, at the moment we don't know yet which one is valid. We executed both in parallel. Now I know the result. The predicate is known. Then one of the two is thrown away, the other one continues to completion. That's predication. I made a typo. It's the first one I made in 2012. I think that's all. Yeah, the current frame marker registers, we don't need to talk about either because you don't know yet exactly what the stack looks like. And if you want to know more about it, on some other of my lectures, I have more detail about the Athenium architecture. Let this be all about taxonomy of computers. How to, given an architecture, how do you classify it? It's a uniprocessor, it's a hybrid one, it's a parallel one. If it's parallel, it's that kind or this kind. You need to understand enough at least to know what does it mean VLIW, superscalar, multi-core, and soon you'll learn hyper-threaded. Thanks for your attention so far. We'll take a short break. What I plan to do then is do some real work. Right now you were just lazy sitting there and you let yourself be inundated by these eloquent phrases coming from, oh wait a moment, no, I meant fumbling phrases. And I set you asleep. So for another 15 minutes after the break, we'll do a little bit of hardcore coding on the whiteboard, and then we'll talk about exactly E, process, thread, type of thread. Okay, let's restart it in 6 minutes.
It's Bill.
Yeah, you deserve gold point. It's pure gold. Don't eat it. What if you eat calories?
Red and everything. That's awesome. Or your party for some sweet. One ball. That's the goal, right?
How does insurance?
I reached out to my homeowner's policy to see if I'd rather go there, but I don't. I think there may be a few companies that do. Like, so like with my book that I found mine, which is a U-Lock, it actually comes with like, I think $1,000 like guarantee or whatever you want to call it. Yeah, but hers was just the cable lock, which they just, and it was all she wrote. So yeah, now I don't know. It's all good though, that's just.
Yeah, I think I've heard on the radio, like some sort of like dedicated bike insurance.
Yeah,
It's
bike
like
insurance.
non-profit, it's just for some bicyclists.
Yeah.
That kind of like is, you get in an accident, it covers like overdose and stuff. I don't remember how much it costs.
Yeah, well, if you get enough people paying in and hopefully not too many claims and losing some money, you know. Did you get all your stuff covered under insurance or not necessarily?
Yeah, we actually, the claims agent messed up, and so we got more money than we should have because she committed, kind of like $1,700 was the total purchase cost of the items that were stolen, not the residual value. So the residual value was actually underneath our deductible, but she told us that, so we would have to cover up our deductible, and then we would get, if we go out and replace the items and submit the receipts, anything above our deductible up to that original purchase value, we would get back. So we did that, and then she was like delaying. I was like, in touch with her, like, I didn't sell a check, have you figured it out? I'm trying to close all this, and then finally I got a phone call, and she was like, so I misread your insurance policy, I'm gonna honor what we've established thus far, but you should not, like, in the policy, you actually don't have how I explained it to you, and so you should only get residual value. We shouldn't be reimbursing you for the original purchase value. In which case, the residual value, because a lot of people would have been lower deductible than the top end of the we actually got it pretty well.
So they still laugh on that?
I did. So did you.
Two iPhones and some jewelry.
You were late.
Yeah.
I got here, I had a you and Norman.
No, because I had to do that. After this with my
You guys did.
and my mom
My husband was like this.
and
Took really old laptops, like really
Oh, yeah.
worthy
You're getting
laptops.
used to it?
And
yeah. No.
like,
Looked over the nice stuff and.
no, like they took an entire drawer of clothes and upended it, and then like stuff like that.
Just trying to look
See,
stuff
I'm
quick so
real-
we get in and
No,
go.
like they took the stuff with
Is he
us, like I
serious,
lost
or
some of my clothes, I lost
You think
her
it kind of Bill
jeans.
said?
It's a little bit.
When was that like break-in? Like what time of the day? Like, you know, was it?
Night.
Just tell him that he's
Neither my housemate nor I were home.
Yeah, that will get him really weird.
Where do you live?
Because you know
Tiger?
that,
Okay. Decent neighborhood or?
Yeah, it's a decent neighborhood. We've been there for a year now, and we've gotten to know all of our
Have you
neighbors,
looked at this
so.
homework yet?
Like right away, I just went around knocking on doors, asking everyone that we knew if they saw anything. And we actually did have one of my neighbors who saw
Actually, looks pretty straightforward.
like a young couple that was standing in our driveway talking to each other, and he was looking out his kitchen window and just kind of like thought, like, oh, that's interesting, like they're not home. I wonder if they're like friends or something. And so he got a really good look on them, and then he saw the girl walk up to the door, knocked on the door, and then he didn't think anything of it at that point and walked away. So we're pretty sure that's who it was. And he was able to give like a really good description of the police.
Yeah.
So, and I just got a call from the detective that they had a couple that seemed to match the description, and they were gonna meet with my neighbor to show pictures. But none of the stuff was recovered. It was just,
Yeah.
I would feel a lot better knowing that justice was served.
Yeah.
I'm actually glad they didn't do anything like.
Okay,
Just
so
instruct. Yeah, they just like took what was visible and left. If they had like turned stuff over and broken stuff, like that would have felt even more.
Yeah.
Yeah.
Time for coding.
Is that?
Time for coding, woohoo.
Yeah.
We'll briefly this shouldn't be new to you, but I want to amplify it. We'll briefly differentiate between value parameters, reference parameters, and pointer parameters. Value versus ref versus pointer value parameters. I assume that's either C out or print out. C out, C++. We have a global int that can refer to int g equal 109. Now we write three functions. Value parameter. Void p int p and we'll call it with v of g. Then we'll write ref parameter. Oh, it has to be C++ anyway. Otherwise I didn't have the option. We call it void R int reference parameter P. Call it with R of G. It should be V. Now V and R are too similar. Call it val. Val. Ref. And another, yeah. Pointer value, which is void eval in star p, and we'll call it with ref of address of g. Sorry, eval. Address of G, and it's in all cases this G here. Okay, couple of questions just to test your blood pressure. So the dot 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 always means nothing else to trick you or to cheat you and defeat you has been done, only stuff transparent to what we're focusing on. See out, if I say print me the current value of G, what comes out? 109. Print me the current value of P, what comes out? 109. Now I do P++. Now see out, current value of G,
109.
okay? Current value of P,
110.
110. And here, see out, current value of G,
109.
still 109, okay? Strict and clear value parameter, meaning assignments to the former have no impact on the actual parameter. Glaringly obvious, because the actual parameter could have been a literal. It could have been, say, 100 plus 9. It is very difficult to assign the value 110 to the expression 100 plus 9. Okay? Meaning impossible. But that is also difficult. Totally clear. No question, unless you raise your hand. Okay, next. Now, again, we do C out of outcomes. Okay. Then we do a C out of P. Okay. No doubt about it, right? 109. P++. C out of G.
110.
Pardon?
110.
Any doubt about it? Okay. But notice what I'm writing here. I'm writing just G, nothing else. No pointer to P, nothing. What if I do a C out of P?
110.
Pardon?
110.
110, right? And also notice, I didn't say star P, P star, or anything else. Meaning the dereferencing has happened automatically, because at this time of compiling, compiler says, well, I need to generate some value. What is it? Oh, I know what P is. P is a reference to some integer. If it is a reference to an integer, it says, well, previously I generated code when there were integer variables passed. I just passed the address. So at the current place, where we think P is, there sits an address. So we need to go to that location, finding the address, go indirect, meaning do a branch into the destination that we pull out there, go to that location, and then we find the integer value. There's a level of indirection taking place because of this one here. But notice what I wrote, just strict P. Okay, then I'll do a C out of G. What comes out?
110.
110. That is all clear. Luckily, most of you did this correctly anyway. Now, third case. C out of P. First of all, is that legal?
Yes.
Yeah.
Yes. What comes out?
Memory location.
The address of where somebody resides. Okay. Can you test whether can you tell me whether the address is correct or not?
Yeah.
How can you tell me? How can you tell me that FF78 is incorrect but FF74 would be correct?
Compared to the other.
You have no clue really where that is. Okay? The whole code is relocatable. Next time you run it, it may be in a totally different location. In general, you can't say anything about the address.
Well, if you give me context and tell me whether it should be pointing to a different value or pointing to the original value, and you give me
Nope,
context.
I'm not giving you. That's all I give you.
Yeah.
And I ask you the question.
Could you print out the address and name of G and see if those two addresses?
Yeah, you could, but I didn't do that.
Okay.
So what comes out here is simply some kind of a machine address. Okay? Chances are in decimal. Nothing magic about it. How about C out of star P? What comes out?
109.
109.
Wouldn't it be 110 at that point?
Pardon?
Would it be 110 at that point?
Yeah.
Because we already changed. Well, if it's sequential.
Assuming this is sequential.
He's
Oh,
going
I
from
see.
main and,
It's a good comment. Okay, same question now. So we assign G109, then we call pointer to value parameter. Actually, I should call it pointer to an int. Pointer to int. And you can. So we assign G109. We pass the address of G, print it out, some kind of a machine address comes out. If you run on a 32-bit computer, hopefully it's within 0 and 2 to the 32nd minus some blah, blah, blah stuff. So now comes out a 109, right?
Mm-hmm.
Now, am I allowed to say P++?
Yeah.
Yes.
Doesn't mean much.
Okay.
It doesn't.
And I'll do it. Now I'll do another C out of P. What comes out?
Garbage.
How do you know it's garbage?
it's
The very
the
next
address.
address.
Or if this is garbage, why wasn't that garbage?
But you incremented the address, right?
Exactly.
So you don't know what's there.
Exactly. I like your comment. It's actually garbage. Yeah. I have no clue whether the data are correct or not. And therefore, as a good programmer, I wouldn't do it. Now I do a C out of star P. What comes out?
Nothing.
Yeah, I don't
Depends
know.
on what's there.
It's the same idea.
Serious. Remember that I've tried in much detail to say all of the other stuff here is not anything that misleads students, meaning there's enough information for a complete picture. So, G is set to 109. I'm passing the address of G. I call the formal parameter P. It's of type pointer to an int.
Well, it's the same thing. You're trying to dereference the garbage memory, so you don't know what's there.
You're correct because of this here. Now I'm striking this.
So
I'm
it's
doing
still
the
P++.
call. I enter the function and I do a P++. Still, just increments the address. Now I don't do this. And we established already this would print me a 109. Now I do a Is this legal?
Yes.
Yeah.
What does it do?
Increments the value. So
It goes to the thing pointed to, increments it, and says I'm done. Now I'm doing a C out of store P.
110.
What comes out? 110. Okay, then I write myself a macro. If not cond. So every once in a while I write an assert. And as a matter of fact, what I would like you to pick up a habit of sprinkling all of your code with assertions. Meaning, oh, at this moment, the so-and-so must be such and such. Well, how do you know whether it's true? The right way to do it is put an assertion that tests for it. Well, that hurt. Then I'm loading up my code with a whole bunch of later superfluous stuff. Yes, indeed, and that's why you say, pound if def debug, do a pound define of assert, pound else, do a pound define of assert, which is nothing. Okay, and then the next time around when you say, oh, my code now runs fine, then you say, that debug is now set to 0. So that you don't need to make any change in your whole code except for one thing. Am I currently in debug mode? Yes. Debug is 1. Otherwise, when you're done, oh, now I'm going to change. Debug is now 0. So that you don't need to change any of the 10, 100,000 or so different places where you assert. Yes, question?
I was gonna say, so the condition is just actually literally a condition that would be evaluated.
Yes,
And it'll
exactly.
just map to the functions.
Now we'll do it. Because now I want to make sure, wait a moment. Am I still thinking about that global thing here? So now I say, I, the programmer, was living under the assumption that pint would be called only with the address of my global. How can I be sure? Well, I cooperated with somebody else, but the somebody else took CS201 at Portland State, maybe a crummy programmer, so I never can rely on her. So therefore, I put in an assertion, assert P equals address of G, comma, should be, where's my eraser? In other words, I sprinkle my code with assertions of the kind, at this place, I think P should be equal to the address of G. And if it is, we have silence. But if it isn't, I get the message, you dummy should be or whatever. And then you provide the value too. I messed this up. So this time I arbitrarily defined a macro of 3 parameters. One is a condition, one is a message, and when the message comes out, I know that I did something wrong, I expected something else, and the thing else that I expected I print as a decimal value. Okay, so these kinds of assertions, sprinkle them into your code liberally. And again, well, but then my code grows so much. When you're done debugging, you set it all to pound debug is 0. And this is in pound if def, and therefore it amounts to 0 bytes. 0 bytes execute very fast on any machine. Okay, there was a question? Yeah.
So does it just do a no-op then, once you switch the assert to being empty?
Say it again?
Does it do a no-op when?
It becomes a no-op
it becomes a no-op
when you turn
it's
it
empty.
off.
Okay.
Yeah. Maybe, okay.
Cool.
I think I'll write it. I was sketching it out because I was thinking it's very obvious. It is only obvious, but not very big. Here's a pattern. Of coding that I would like to encourage you to use word appropriately. I'm sketching again. What's the end of pound if def? Is it end if or end if def? So that means you haven't used it. Yes, I have used it many times, but that was millions of years ago when I was your age. So, and I think it is end if, but I'm not quite sure. You need to look it up in your manual. And then comment. So that's the pattern which I encourage you to use. So first of all, make your code switchable and switch it on some kind of a state. I'm alluding to debug state or not debug state. And there are many other variations. So sometimes you want to optimize for speed, sometimes you want to optimize how this is a chess program for advanced people, sometimes, and you get the drift. Then you can use this Boolean in if def. If def is defined to something different from 0, then do a whole bunch of things, as many count defines as you want. End of it, no more continuation. Else, this is now the else to the if-def. And make a comment here that this else belongs to the if-def debug. Then you can do something else, such as define, assert, open, close paren, nothing. Actually, because you will have parameters there, it is more accurate to say C, comma, something similar. But they don't have to be the same. Call it C1, M7, and V8. Okay. I will now find in my code an assert thing with 3 parameters which map into nothing, into empty strings. Every time that your C compiler finds assert, double quote, open paren, x equal to address of foobar, comma, double quote. Hey buddy, you made another error, double quote, comma, address of G, close paren, semicolon. All of that maps into nothing in this case. Okay, so I encourage you to do that if you care about programming. All right, one more case. Shoot, put it up in there, I thought. Did I confuse somebody here? A little bit? What's unclear?
It's kind of practice we would never use this for. Never done.
Okay, but the logic is clear. I want to put in a whole bunch of assertions and not overload my code with assertions. Right? So therefore you have 2 different modes of compiling. This is how you parameterize your mode of compiling. Next time around when you say, ah man, because I'm such a good tester, I've tested all cases and I've proved to myself logically that it's always correct. Then you compile it again and you do 0. Strictly speaking, you would also be allowed to say come to find DB, nothing. That would be okay too. Who else is confused? Come on, you're giving me a job to do. Okay, this is boring and simple stuff. Now comes the interesting stuff. Now we'll do
Right, so and every place in the code that you put in a search statement, it's going to run.
What do you got? It's okay.
Wait, that's what it's So, otherwise, you're not going to. So,
Okay, big something. In C, all parameters, with one exception, we'll talk about it in a second. All parameters are passed by value. What is the exception? Arrays. In C++, which is compatible with C almost 100%, not quite. We have the same parameter passing mechanism, plus we have reference parameters using the ampersand operator. So the key difference then is that explicit reference parameter. So I'll talk about one of the 2, but not both. I'll talk either, you tell me what you want more. Either I show you and we'll discuss how even structures can be passed by reference in C++, because that's different from C. Or I show you how arrays can be passed by value if you pack them into a struct. Which one do you want to do?
What was the first one?
Arrays by value.
The first one is, remember that in C everything is passed by value except for arrays. I want to force now, and in C++ I can do it, I want to force that my struct is passed by reference, which is an interesting case, somebody might think. So we either, you tell me.
The second one.
Both.
No,
no.
Neither.
I don't have enough time. Either a struct by ref or an array by val. Which one do you want?
Array by value.
Array by value.
Okay, forget about this one, array by value, but in that case I have to pack the array into something else, because arrays are passed by reference. But I still want to pass it by value, so I need to package it into the struct. Totally clear? We'll do that. Okay. All right, for a moment I was preaching, and I'm not embarrassed about my preaching. Make your code flexible and checkable. Checkable with assertions, flexible that the assertion don't clutter up your code in the end. The other thing I'm preaching is whenever you define things, variables, objects of some kind of a type, and you use the same type 2 times or more, what am I going to preach now? Use a type def. So first of all, I'll define some kind of array type. My recommendation for your homework number 3 was to use matrices of size 15,000 by 15,000. That's a good sized array. By no means big. Real arrays are million by million. So define size 10,000. Type def. I want to define now int arrays of that size. So type def int array type of size. Every once in a while I do make those syntax errors, so you check them. Students, what I've done now is I've defined a type by a symbolic name called ATP. That's my brief for A type. And any object of type A type is an integer array of that size. Totally clear? Now, since you told me I have to stack arrays into structs, not a silly thing to do. It's a good thing to do, happens all the time. I do another type def of a struct. And it has a whole bunch of fields which I now am not interested in, and therefore I will omit them, except for one field. And that is a field of type integer array. And here's the symbolic name I refer to. A type is my array. Now I need to give this thing a name, and is it a structure array or an array structure? Well, it's a structure which contains at least one array. So I call it a struct array type. Here is the symbolic name for another type. The type is, I'm a struct which has one and no more fields. The name of the field is ARR, and the type is integer array of that size. Clear so far? There are at least 2 or 3 of you who say, well, I haven't been too familiar with type defs. But Herb's preaching is, become familiar with type defs, use them all the time. Especially if you use that type or that type more than one time in your program. And if you write real programs, you'll use whatever type you talk about more than once. Therefore, use type defs. But I'm sure Carla or somebody who taught you programming has rubbed that in galore anyway. So I won't repeat it. Now we'll define some object. Here's my structure array type A. Somewhere I have a function, and I'm not putting the function name here, where I write code to initialize it. So for int I equals 0, I less than size I plus plus. I want to initialize each element of the field of the structure to which value? 109, of course. So the name then is A. What am I going to write next? What am I going to write next? You play. Students.
A, brackets.
Dot, right? It's a struct.
A dot R.
A is a struct. It has more than 0 fields. To get to the fields, I say dot, and then what's the next thing I write?
R.
ARR. What's the type of what I've written so far? A dot ARR. What is the type?
A underscore TP.
Some of you started right. What's the type of A dot ARR?
A underscore
A
TP.
underscore.
Array of int. Okay? It's an array of int, but exactly size of the ints. Sub I is assigned 109. Or any better number that you know according to the logic of your current program, and I don't want to write it out. Dot, dot, dot. So, I'm writing the dots here, same preaching. Nothing mysterious is happening. Nothing does the teacher put in there to trick you into wrong answers. It does not happen. Not today, I'll do it tomorrow, but not now. Okay, now we write a function. Or we see how smart you are. And, oh, now I forgot, what did you want? You wanted,
An array by value.
oh, you must have wanted the array by value, yeah, because that's why you packaged it into it. So what's the type I'm going to use now?
SATP.
A struct that has an array, that type, and I call it my local. Array in struct passed by value. And smart. Now I continue. And somewhere I call smart with A. All right. So all of this has taken place. This function we are not executing now unless called. Here's some other functions. We skip them all. There's the main program, and in main we are calling now smart with A. Is the scenario clear? We haven't done anything yet. Now we are calling smart. We enter right here and do our first thing. So, what's the value of local? What's the next thing I write?
Dot R.
Dot. What's the next thing I write after that?
R.
ARR. I want to see the value of L.ARR sub 5. What is it? 109. Yep. Now, I say L.ARR 5 plus plus. What's the value of L.ARR sub 5? Now,
One time.
Totally clear, right? Now, what is the value of A dot ARR sub 5?
109.
109.
109, because we passed all of these things by value. Whatever we do assignment-wise here to the local value parameter has no impact on the actual parameter. That's what value parameter passing means. Completely clear now? Okay, then, quick question. If I write my old assert there, I'm writing now assert, this is wrong too. I think, correctly or erroneously, I'll leave it up to you. Assert the address of A equal to address of L, must be same. Do I get an assertion error now or not? Remember, I'm using the same assert that I defined over there earlier. Do I get an assertion error or not?
Yes.
Definitely, big time. They are not the same, these two addresses. This is an address somewhere in static memory. The address of this thing is an address somewhere on the runtime stack. No way are they ever the same. Okay? So, just another quick reminder of how good an assertion will be. And that's all I want to do. The reference parameter struct, by now you should have it totally in. Okay, then we'll start. I still have 9 minutes. Tell you what, I'll at least start with the next topic. So, if I start with the next topic, then the whole class in one day. It's 10 minutes off. Here's what I do. I'll break down and I will discuss the reference struct anyway. Could be done in 2-3 minutes, and then we go home. Okay. I still want to have an integer array type. I still want to have a struct that has an array in it. I'll use it using a global variable. I initialize it, and this is my last test today. And I'm going to call, oh, it's a struct. So the type here is structure which has an array, that type. So normally L would be a structure, but now I make L a reference parameter. What I wish to do is, I wish to bind the parameter of last, my last test, with this globally visible structure that contains at least one array field. How do I do that? So in my program, I want this L to be connected with this A. How do I do that? At the call? Is it clear? Ampersand of A. Any question?
What's the address of, instead of, like when we pass.
What do you think, students? I must be tricking.
That's wrong.
Is it right or wrong?
That's
It's wrong. That's the nice feature of the reference parameter. Okay, your C++ compiler is strongly enough typed to say, oh, you are going to pass something to a reference parameter of type SA type. A is of SA type. Since it's a reference parameter, I, the compiler, know that I don't have to make a copy of the thing. I simply pass the address, even though you didn't say ampersand of. Okay? If I had said pointer here, and I still want the thing to work, then I would have had to pass address of A. But in C, I don't need to. In C++, I don't need to with reference parameters. And now let's